All right, so here is the exam review, and I'm going to work some problems like what you might find on your exam. Take for example this, let's just do problem 1 right here. Find the marginal average cost and evaluate it at some number. Well, there's a difference between having the average cost and then taking the derivative of it versus having the marginal average cost. This is supposed to be C prime of x over x, and so this sort of indicates to us that we need to find the marginal cost and then take its average. So our function is 161 plus 7x. If I find the marginal cost, then that would just be 7. That makes sense to us because this is just a linear function, just increasing by 7 all the time. Or for every 1 unit increase in x, we have 7 units increase in c of x, which is what this is trying to express. And then so the marginal average cost would be 7 over x. Stop it, kitty. Kitty's trying to bite my pen. Okay, and when you evaluate that at 10, you get 0.7. I would maybe be looking to get some kind of quadratic if I was on a test. If I was writing a test, I would be looking for a quadratic function to give you instead of maybe just a linear function. Okay. It's a real important estimation tool to understand, so looking at this graph and questions 2 and 3. That's what I want to do now. So when you're looking at this graph, the difference between these two x values is just 1, right? Between 50 and 51, they're just 1 unit apart. In fact, this expression, my interpretation of this expression is that it is the revenue generated by the 51st item. So it is the precise revenue that was generated by the 51st item. In fact, it's just 5095 minus 5,000. So there I have found it. It's $95, and the sale of the 51st item brought in a revenue of $95. Okay. Part A of 3 it says, suppose the company knew the revenue was 5,000 when 50 units were sold, and that the marginal revenue at 50 was 96. Use this information to estimate the revenue from the sale of the 51st unit. If there is something for you to screw up on this test, it will be this property of doing this estimates. If I have knowledge about what's going on with the revenue at the 50th item, well, let me back up. We already established that R of 51 minus R of 50 is the exact cost, is the exact revenue of the 51st item. Is this computation, 95 right here, is the exact revenue of the 51st item. But it is also approximately the marginal revenue of the 50th item. Because that's exactly what our interpretation of this right here should be, is that it is the estimate of how much the revenue would be for the next one. And if you can produce this relationship, then you can rearrange it when you only have this number and this number. So then R of 51 would be approximately it would be the revenue brought in by the 50 units plus the revenue brought in by the next one. And it says that should approximately be the revenue of the 51st one. Okay, super. Well, we knew that R of 50 was 5,000, and they told us that here we knew that this was 96, so we're getting approximately 5096. And that's only $1 more than what actually happened. And I think that covers question B as well. I mean, question B that's putting the horse before the cart. You gotta know what you're doing. You gotta know the answer to B before you can do A. Alright, the answer to B was us writing this relationship and then rearranging it to be solved for the thing that we're curious about. Alright. So, let's see what else we got. How about some relative rate of change of the... So there was this question in the notes during class, the lecture notes, when they introduced, I don't see one here, when they introduced the idea of elasticity of demand. Before they could do that, they had to talk about relative rate of change, and the abbreviation that was chosen was RROC, the relative rate of change. And that this is really not anything more than, so the relative rate of change of some function g is g prime of x over g of x. And this question that was in the notes was a motivator. It was a question leading us towards a motivation for why we would want to ask about the relative rate of change. And it was a question about which investment strategy would you choose. If I had a hunch that this stock was going to increase by such and such amount and this other stock was going to increase by a different amount, but they're at different price points, which one would be the better bargain if I somehow could guarantee that they would perform as predicted. So if stock A let's say is going to have a 100% increase, in its price. Over some period of time, then that would correspond to the relative rate of change being just 1. 100% is the number 1. If stock B was only going to have a 10% increase over that same time, then it would be very obvious to you when I'm stating it like this that this is the better investment choice. You know, what might simulate this? Well, if the price per share was $300 and you knew that it was going to go up by $300, and that's a 100% increase. But if it was only going to go up by $30, then that is just a 10% increase. And so the relative rate of change, you know, clearly this one had a bigger rate of change because it changed by 300 units. This one changed by 30 units. But relative to where it started, this one had a much bigger rate of change, and so you would choose stock A. And they use this notion of relative rate of change to construct the function for elasticity of demand. Because you have your demand function. So you have your price demand equation, D of P, and then this writing is the relative rate of change of D of P, but then for just our variable P, differentiating with respect to P, you would get this statement as the relative rate of change of P in P. And when you do some simplification, and they toss a negative in here because E of P always comes out negative if you don't define it this way. They like for us to tack that negative onto the front of it, so it's a minus P D prime of P over D of P, and this puts E of P as non-negative. In fact, it's positive, strictly positive. And you have that cutoff point where if E of P was 1, then that's where revenue gets maximized. Okay, I'm doing a lot of talking and not a lot of problem working. Let's see what we've got here in the book, or the examples. Sorry, this is like the first video I'm making since I got so sick, and I know I'm feeling a little out of sorts still. Let's do this number 104. If this is our relationship between price and units demanded, they just say find the elasticity of demand, E of P, and we'll find it and we'll answer some questions about it. So the demand function was 12,500 minus 225p. It's a linear function. It's basic enough. This is equal to the number of units demanded. So even if you were giving it away for free, the demand would be capped at 12,500. Demand could never be higher than that. Okay, so d prime of p would just be minus 225. Then E of p would be minus p, don't forget that part, just write it down first, times d prime of p minus 225. Notice how my negatives are canceling. This is happening because we put this negative here, forcing E of p to always be a positive number. I've seen it in books where they don't do that, and they just leave it negative. So be prepared to encounter that one day. You cannot do this cancellation. Don't do that. Please don't do that. You're in calculus now. You should be knowing that you can't make this cancellation like that. Right? I have a sum here in the bottom. I can't just cancel unless I factored the p out of both of these terms in the bottom and cancel it with the one in the top. But I can do some simplification because 12,500 shares some factors with 225. I guess I'll factor out like 25. So here I'd get 9p over 500 minus 9p. I guess that's as good as I can factor it. Well, where does revenue get maximized? That's where the numerator and the denominator are the same quantity. So that's 9p being equal to 500 minus 9p. Add 9p to both sides and then divide by 18, then p is 500 over 18. So to maximize their revenue, they should set the price to $27.77. If the price were any lower than that, then excuse me. If the price were any lower than that, well, it's a challenging question to find the price, or it's a more challenging question to find the price that puts E of P between 0 and 1 and 1 to infinity. But if I look at this writing of my function E of P, and I want that thing to go to infinity, So E of P will go to infinity as 500 minus 9p goes to 0. That has got to be the case, and so this would be the same thing as when p goes to 500 over 9, which is what, double this quantity here. So then what we've actually found is that we've got E of P in between 1 and infinity whenever P is in the interval of, I'll just say 500 over 18 all the way up to 500 over 9. And you can just do the same thing when it comes back to if you wanted to find where it was inelastic. I seem to always get them goofed up. When it's equal to 1, we call that unit elastic. And yeah, if it's bigger than 1, it's elastic, I think. And then less than 1, inelastic. So you can raise the price, and you will increase your revenue. And remember that increasing a revenue or maximizing a revenue should not usually be the goal of the business. Usually the goal of the business is to maximize profit. Let's look down here and talk about some increasing, decreasing stuff. So maybe we have a function and we want to find the intervals where it is decreasing. I don't really see anything that is just what I like, so we'll just make something up. I want to just have a function. Oh my goodness. That I have to quickly engineer a function that can be easily differentiated and the result would be able to be factored by you. So let's try this one on. So if this is my function f, I want to find all the intervals where this function is increasing. Well, that would mean I would need to find my derivative function, because it's going to tell me all about the slopes of the tangent lines. Oh, let's see. Oh, okay. Well, there we go. and I can see that an x squared factors out, and then I'm left with x minus 36. All right. Then I would make my number line drawing. And put all my critical values, 0 and 36. Now the sign will change right here at 36 because of it having this term in its factorization. You know, if you picked a number that was between 0 and 36, like 1, 1 minus 36 would be negative, and it'd be a negative times a positive. So this is just negative right there, but it switches back to positive here. But going over here to the left side of 0 won't cause you to have any change, because this x term is duplicate. You can try a test point if you want. Try to put in minus 1. You're going to have negative 1 times negative 1, that's positive, and then you put your negative 1 right there and you get a negative number. And so sure enough, we saw no change in the sign at 0. Now since this is a chart about f prime, then what I really want is my increasing and decreasing arrows. It's decreasing here and here, but it's increasing here. So where is this function increasing? On 36 to infinity. All right, I'm going to pause this and take a little break. Let's make sure we know what all of our derivative tests mean. So the first derivative test was a way for you to determine the slope of the, you're using the interpretation of the derivative as the slope of the tangent line, and then in turn that is telling you if the function is increasing or decreasing. So if the slope, that'll never happen. If the slope is positive, then you know that the function is increasing at that point. Maybe I shouldn't write slope. That's really the slope of the tangent line, and the slope of the tangent line at a point x is f prime of x. So f prime of x greater than 0 would tell you that f is increasing, and if it's less than 0, it's decreasing. If it's equal to 0, all you know is that the tangent line is horizontal right there. The first derivative test is helping you to understand that if you have a scenario where you change sign of the derivative with a spot in the middle where the derivative was 0, then you have a local extrema. So if I can get squeezed in here in the middle that it was equal to 0 at this point, well, I don't exactly like my notation here, but so we'll say it like this. If I'm to the left of C and it's increasing, and then right at C it goes horizontal, and then on the other side of C you have a opposite slope, then all three of these observations together describe for you the behavior of this function right at the point C. Is telling you that it's increasing, it goes horizontal, and now it's decreasing until you have a local max. Likewise, if I had taken a second derivative here, then my second derivative here would have the property that it is less than 0. Just telling you that it's concave down. Actually, we're checking right at C. F double prime of C is less than 0. So that means it's concave down there. Well, then it becomes enough. It becomes enough to just say that you really only need to check two things. Number one, that f prime of C equal to 0, and number two, f prime of C, we'll say, I guess, different from 0. Then these two things together can tell you if you have a local extreme. Because right here, f prime of C was less than 0, so it was concave down at a critical value. That's all it is. If it's concave down at a critical value, then it makes a maximum right there. All right. So, be prepared for some conceptual questions like that. And in particular, that you can interpret the charts that we would use to make the sketches of our functions. So ever since the first week of class, we have been making these number line charts. It started off by us just wondering where the function f was equal to 0 or undefined, but now we're wondering where the function f prime is equal to 0 or undefined. So I'll pick, maybe these are my critical values. Maybe it's undefined here and 0 here and and 0 here, let's say. And if they say the sign, if they say that these are the signs in each of those intervals, then I can immediately translate that into increasing and decreasing, right? Because the plus and minus is just telling you that what's the behavior of the slope of the tangent line. And since I changed from increasing to decreasing and had a spot in between where the derivative was 0, then you have a local maximum right here, you have a local minimum right here, and probably an asymptote or something right there. Okay. I guess that's all I want to say for now. I'm going to stop this video and start a new one where I'll cover the rest of what might be on the exam.